Alright, so this is meant to be a walkthrough of what we did today in class on was October 28th, and what I will be doing on October 29th with the B schedule students. So for those of you stuck at home, this is meant to be, the first half of this was meant to be a refresher for horizontally launched projectiles, brief overview of what the rest of the week will hold, and then I wanted to start projectiles at angles, and I'll begin that with the last couple of minutes of this particular one. I'll at least walk through one example so you've got it in your notes and you've got something you can then go back and reference from there, hopefully once you see the process and see the steps, why I choose the equations that I do, or why I give you the exact equations that you should use in those procedures for solving those kinds of projectile problems might make a little bit more sense. At least that's the goal. So for assignment 4, this is where we started in class today, and we've got Homer Simpson driving down the road at 40 meters per second, reaches the edge of the cliff. It's a cartoon, he's going to be fine, but one of the things that is oftentimes the best thing to do whenever you've got a projectile problem, whether or not it's a car going over the edge of a cliff, or someone throwing a baseball or a softball or whatever it is, it's usually a good idea to draw a picture, right? Now, I spent a lot of time drawing my cars, as you can clearly tell, but when this car goes over the edge of the cliff, there's really only one piece of information so far in this entire problem on assignment 4 that has been given to us, and that was the horizontal velocity of that car. And the horizontal velocity was 40 meters per second. Now, I like to label my horizontal velocities with V and a subscript of an X to remind myself that it's in the horizontal direction. But then they wanted us to draw carefully, and this isn't something you're going to have to do on an exam, but it's a really good way to connect the concept to why we use the equations that we do, the path the car that it's going to take on its way down. The path that this car is going to follow is the same as every other projectile that we've looked at so far. It's going to have that half circle parabolic sort of trajectory. And that's not going to deviate, right? Whether or not I am rolling an object off the edge of the lab table in the front of the classroom, or it's a car going to the edge of the cliff, or the Mythbusters fire a bullet from a gun that is sitting horizontally, like in the video that we watched at the start of this unit. They're all going to follow that exact same path. So, question number 2 asks you at various ways along the path, how does the magnitude of that value, your horizontal velocity, change? Basically, after 1 second of being in the air, I'm just picking a random point to be 1 second, has that Vx value changed in any way, shape, or form? The easiest way to think about this is that was his speed, Homer Simpson's speed, while he was driving across the road. And the moment he's no longer on the road, his wheels have no bearing, his tires have no bearing over his ability to speed up or slow down. So what we would normally do, if you wanted to speed up and go greater than 40 meters per second, you would hit the gas. You would accelerate and you'd be traveling faster because your tires are pushing harder off of the road. But the moment Homer Simpson is airborne in this scenario, he cannot speed up. Likewise, he cannot slow down, right? If he's mid-air, airborne, as we like to say, and he decides 40 meters per second is too fast, but he's already a second into his fall, there's nothing he can do. He can hit the brakes, he can pull the emergency brake, he can do whatever it is any normal person might try to do in that sort of scenario, and there's nothing you can do. Once you're moving, like sliding on a patch of ice, you're going to keep going in that direction at that speed until something else stops you. And so that's what we're trying to get at with number 2. Is how does that change? And the answer is that it doesn't. Your horizontal velocity doesn't change in any way, shape, or form at any time throughout the course of this trajectory. If you want to use physics language, if you will, for that, it's because your horizontal velocity is 0 meters per second squared. You can hit the gas, you can hit the brakes, and nothing is going to cause that car to speed up or slow down horizontally. Just like the bullet fired from the Mythbusters gun, once it left the barrel of the gun, it was not going to speed up or slow down as it moved horizontally. The only thing that causes anything to speed up or slow down at all is the acceleration due to gravity. And it causes all things in the vertical direction to increase by -10 meters per second every second. That's what gravity does. So 1 second later, now, instead of starting with 0 vertical speed, now this car has got some sort of negative velocity, and it's going to be pulling it slightly downward, which is why this path eventually and gradually starts to bend and change direction, is because the longer it's in the air, the bigger this vertical velocity vector becomes, right? 1 second later, it's -10. 2 seconds later, it's -20, so on and so forth. So if the cliff were 100 meters high, one of the things that might be beneficial to you guys, and there's multiple ways you could do this. I've shown you diagramming in the word problem, how to label your variables and keep track of what you know. In this particular unit, you can draw pictures to keep track of what you know, or you can make data tables. You can make a data table out of your y values and your x values, or you can make a data table like this. Things that you know to be true at the beginning of the problem and things that you need to know. That's what NTK stands for, need to know. But the process is still the same. We start with the y-axis. We will always start with the y-axis, just like we did in the notes on Monday. Things we know about the y-axis is that our vertical displacement, this car that Homer Simpson is driving is going to fall, is 100 meters. We know that's how high the cliff is, so he's going to fall from 0, where he started, down 100 meters. Now, other things that we also know is that the vertical acceleration is going to be -10 meters per second squared, right? That's gravity. Gravity only works in the vertical direction. We also know that because Homer Simpson's car wasn't going up and off a ramp, your initial velocity in the y direction, because you can have velocities in both y and x directions. That's honestly the most complicated part of this particular unit. The initial vertical velocity, up and down, because he didn't get launched off of a ramp or fired down at the ground, is going to be 0. So really the only thing we need to know, and the main purpose behind using the y-axis, literally the ultimate goal, if you go back to the cover page, it says, step number 1, you're going to use the drop equation to solve for time. You need to figure out how long gravity will allow this car, in this particular case, to be in the air. Once you know how long gravity will let it be in the air, then you can figure out how far it's able to travel in that amount of time. But ultimately, it's gravity. The Earth's gravitational pull determines how long something can be airborne, and really no other factor outside of adding wings, a parachute, or a rocket is going to alter that, right? If you're in free fall, gravity determines how quickly you're going to hit the ground, and that's it. Which is why we always start with this equation. dy is equal to 1/2 ay t squared. I forgot my y. Again, it's the same as d equals vit plus 1/2 at squared. I just left off the vit part because this was 0, right? We don't need to include it. And then all I did was get specific with the vertical distance I'm dealing with and the vertical acceleration so that I don't accidentally start plugging in horizontal components into this equation, because gravity doesn't work horizontally. If I'm using gravity, then it's got to be in an equation that is only dealing with the vertical components of stuff. So in this particular case, I'll walk through all of the lines of math to help you guys out. We've got 100 is equal to 1/2 of -10 multiplied by time squared. I'm going to leave the -100 alone for now. 1/2 of -10 is -5. That is multiplied by t squared. Divide both sides by -5 because it's -5 multiplied by t squared. This is going to give you a positive 20, which you need that to be positive because you cannot take the square root of a negative number. We're left with t squared. Remember, 20 is not the end of the road, so you've got to take the square root of both sides to get rid of the square. And I'll put it up here. We're left with a time of about 4.5 seconds. That 4.5 seconds is the courtesy of gravity. Gravity allows this car to be in the air for those 4.5 seconds. So that means that this car is also able to travel in the x-axis horizontally for only 4.5 seconds. So the first thing I'm going to write down that I know is that it's moving left and right for 4.5 seconds. I also know that my horizontal velocity from the very beginning was 40 meters per second, and that I have absolutely no horizontal acceleration. Because I have no horizontal acceleration, this is the only reason we get to go back to using our nice, neat, old equation that we all liked. The one without acceleration incorporated into it from Unit 2. This is the only reason I get to use that equation again, is because when it's moving left and right, gravity doesn't cause it to accelerate. And again, barring wings, a parachute, or a rocket attached to it, there will be no horizontal acceleration of any kind for any of the problems that we're doing at all. in this class, actually. You know, maybe some higher level physics when you get to college, that will be an issue, but here it certainly will not be. So your horizontal distance is equal to your 40 meters per second multiplied by the 4.5 seconds. And in this case, that's 180 meters is how far this can make it in the 4.5 seconds gravity allowed it to be airborne. Now remember, it always comes back to gravity allowing it to be in the air for a certain amount of time, and then from that amount of time we figure out how far it can go. This is going to be the same procedure, the same set of steps every single time. So the top of this worksheet was really just the conceptual, hey, this is why we're doing this way. And then the bottom part of it, 3 and 4 here, these are the 2 steps we're always going to be doing in our horizontally launched projectile problems. You're going to have step number 1, dealing with the y-axis, finding out how long gravity lets that thing be airborne. And then number 4 is basically your step number 2. Now that you know how long it is allowed to be airborne, that's going to tell you exactly how long it is, how far it's able to go in that amount of time. So what I progressed with for the students that were in class was a quick summary of what is to be expected. You don't have to worry about anything on page 9. There was one data table on the exam. It was a very short part of the problem. I am going to get rid of that entirely. It was like a second alternate way to solve the problems. And not many students have ever historically chosen it, so I'm going to leave that out for now since we're short on time. Assignment 5 is going to be your homework for Friday, but I want to point out that there's a couple of tricks, a couple of things I want to remind you of as you go to do it. It's really good practice for the quiz that you guys are going to have tomorrow. So this 80 meters right here, I'm going to write down, don't use it. I don't want you to use that 80 meters. You're still going to take the horizontal speed of 35 meters per second. You're going to take the vertical height of 205 meters, and you're going to find out how far it's able to go, just like you should have before. Notice this is scaffold. I use the same scaffolding is what I'm looking for in this particular problem that I did in the last couple, but I'm starting to step back and just kind of give you a basic problem all by itself. I don't want you to use 80 because that's just where the water begins, and the last question is, do they make it to the water? So use the distance that you calculate, just like we just did, and if it's over 80, yes, the car made it into the water. If it's under 80, no, the car did not make it into the water. That's all I'm looking for, so give me the distance. Because we're not worrying about those data tables, I'm going to take it off the exam. You can skip that. That is not something that you need to do. Question number 2 on assignment 5 for Friday at midnight is basically what you'll see on the exam. It is your 2-part horizontally launched projectile problem. You got Santa Claus being lazy, throwing presents out of the sled instead of getting out, whatever, right? But the idea is that the present is the projectile. It's moving at this particular rate. Do with that what you will. It's to this distance above the ground. Do with that what you will, just like we're supposed to. But find out how long gravity lets it be in the air and how far it will go horizontally in that amount of time. That is the goal. Number 3, this one's going to be a demo that I'm going to do in class. I'm going to record for you guys on Friday. For those of you who aren't going to be here, we are going to use these 2 values, and I'm going to get rid of the question that was like this on the exam because we're obviously not doing the lab. You're going to use this 43 centimeters in 1.32 seconds to find, to find your horizontal velocity. It's a really ugly VX. To find your horizontal velocity as this ball travels, I'll clean that up, it's just going to bug me. To find your horizontal velocity as this ball travels across the table. Once you find that horizontal velocity, don't use 43 centimeters or 1.32 seconds yet, right? So you're going to use it down here to find VX in letter A. Then it's the same 2 steps you've always done, right? You're going to use the height of the table to find out how long it was in the air, and the distance away that it's able to make it in that amount of time, you're going to use that VX you calculated from before. That was supposed to be your lab. Me and the other physics teachers have beat our head against the wall for the last month trying to figure out how we're going to do that lab with all the COVID restrictions that we have, and we just can't figure out how to make it work, so I'm going to do it as a demo. It's a lot less exciting, but you're still able to see the practical application of the theory that we're talking about here. So that was number 3. Please make sure, real quick, that we convert these centimeters into meters because gravity is meters per second squared. So answers are down below, and that one should be pretty straightforward. The next video I'm going to make is all about projectiles for assignment 6. So I will be making that one probably tomorrow during my lunch or before school, one of the two. And I'll be posting that as soon as I can to help you guys out with projectiles at angles. But that was about it. I wish you guys the best of luck with the homework. Please, 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 as always, reach out with questions, comments, or concerns. Don't feel like you got to do this alone. I will answer anything pretty much at any time of the day. See you guys later.